Okay, let's get started. We have some unfinished business, and then we're going to talk a little bit about dot product, and then we're going to talk about the test. That's our plan. So last class we stopped in the middle of a problem and talked about the test a little bit, and someone was asking about it being a bonus question, and I said no, and the reason why is because, well, you're about to see. So we had this situation. What was the weight on the 200 pounds? So we had a rope. It was 5 foot. And then we had a 12 foot like this. And then we had this weight attached to these ropes of 200 pounds. And the question was, what was the tension in each of the ropes, right? And we started to try and come up with triangles and do things and figure it out, right? Yeah, we couldn't. We had one equation and two unknowns, and at that point, we were stuck, and we would have continued to be stuck. And here's the reason why. Imagine that we draw this scenario again. Could I change this picture in any way that would change the tension on the ropes? In other words, can I change the shape of that triangle? Could I take this point and move it to the side? Yes, if I take this point and move it to the side, still maintain the 12 here, that'll change this angle and it'll come up a little bit, won't it? So it'd look, maybe something like this. In other words, there's not a unique position that we could have this in. And we need a unique position in order to be able to come up with the tension on the ropes. So I need to add one more piece of information to this in order for us to be able to solve this. So I went ahead and I'm going to add one element to this. Let's make this distance 15. Now you can't move those points around. Do you see the difference between the two pictures? Okay. So if I add that there, then we can do this. All right. Now the book does not give you a problem like this. In the problems in the book, they just give you the angles of these ropes, which is an easier problem to do. So this is a little more advanced than what the book is presenting to you. But we can still do this, all right? So we have two ropes. I think we were starting to call them rope 1 and rope 2, right? It's a vector this direction, R1. Another one in this direction, we'll call this R2. And then we have the weight of the weight itself, which we can call, did we call it something last time?
No, we just put for B.
B? G? Okay. It was what?
It was B.
It was B? Box? Okay. All right. So we have these three vectors, and what we know is that the sum, if we add up the forces in the x direction, it should be 0. If we add up the forces in the y direction, it should be 0. And I had also told you that, like in a physics class, that's this very common formula that looks like this. That's basically saying that for objects that are static, not moving, that the sum of the forces in the x directions must be 0 and the sum of the forces in the y directions must be 0. It basically allows us to set up two equations. Right? Good, good? All right. Now, in order for us to do this, we need to be able to break down R1, R2, and B into its components. So I need to be able to somehow figure out what the x component of this vector is and the y component, the x component, y component, x component, y component, right? Now, can you tell me the vector B, what its x and y components are right now without even having to do anything? Okay, so the components are, the x components are 0. What's the y component? What's the downward 200, right? But it's down, so negative 200. Is that clear? Okay. Let's go after trying to figure out what R1 is. What we're going to need to know in order to do this is the angle that the vector R1 makes. So what is this angle? And I'm saying relative to, this is almost being like the x-axis. What is this angle for R1? And then we'll also need to find the angle for R2, which will be this angle. And the only way we can get those two is to somehow use the information about this triangle. Right? Use this information. So is there a way that you can get me just one angle in that triangle? How?
Law of cosines?
There you go. That's it. Law of cosines. You have all three sides of this triangle, don't you? So let's take that triangle and just draw it to the side over here. Am I recording? Yes, I'm recording. Okay. Let's draw that triangle over here. And 5, 12, 15, right? And let's label these. How about this is little a, this is little b, this is little c. That way it corresponds to our formulas. And let's go after this angle capital C. Let's go after capital C first. So there was a formula that we used for this, right?
Yes, there it is.
I'm not quite sure which one you remember, but we did have a formula for capital C. It was cosine capital C. Cosine capital C equals something, right? But I'll remind you of the law of cosines. Here's the original law of cosines.
B squared, a squared plus b squared minus c squared over, well, yeah, you're using the law.
Yeah, so this is the original law of cosines, and then we can solve it for cosine C. So we move things around and solve, and it comes out to be cosine C equals a squared plus b squared minus c squared
all over
2ab. That's the formula for cosine C. And then what we'll do is we'll take arc cosine after we plug in all these numbers.
Why do you take our cosine afterwards?
Because this tells you what cosine of C is. It doesn't tell you what C is. So to undo cosine, I have to do arc cosine.
Okay.
So I get my calculator out because I'm going to need it. And we're going to plug in. We're going to plug in for A 5, B is 15, and C is 12. So here we go. 5 squared plus 15 squared minus 12 squared. I get 106 up here. Divided by 2 times, let's see, A times B, 50, what's that, 75 up there? 5, so 150. Okay, so divide here. 0.70666666. Cosine C equals 0.0, not 0.0. Cosine C equals 0.70666. Yeah, and now you do arc cosine on both sides. So I am in, I'm going to be in degree mode here. All right, I'm going to be in degree mode, which I am, okay. And arc cosine of that, 45.035. It's not exactly 45 degrees. 45 point, I'm going to go with 0.4 degrees. Okay? That's C. So in here, this angle right here is 45.04 degrees. Now, we can find any of the other ones now.
Yeah, use a squared.
We can use the law of cosines formula again if we want, or we can do law of sines. It doesn't matter. I did tell you that the law of cosines formula, there's a lot of stuff here that you might mess up, but when you get your answer, that's your answer. If you use law of sines, remember there is possibility of 2 different solutions. So do y'all want to just go with cosine again, just to be safe? I'm going to change this to A. which changes everything here.
BC.
BC minus A squared, so B squared, C squared minus A squared, and then on the bottom, 2BC. And if I do that, then I should be able to get my cosine A. So B squared, 15 squared, plus 12 squared, minus 5 squared. I get 334 on top, 344, sorry. And then on the bottom, 2 times 15 times 12, right? 360. So here's what I have for this one. Cosine of A equals, I'm getting 0.9555 forever. And then I do our cosine of that. Any questions? A is what? 17.14 or 15? Let's go with 17.15 degrees. That was A. That's this one right here, right? So 17.15 degrees. All right, now once I have two angles out of a triangle, I can get the third by default, right? Just by subtracting those two from 180. But do I actually need this one? I don't know if I'm going to need that at all. Okay, but let's just rest assured we could get it if we wanted to. All right, let's talk about R1, because we need this green angle, don't we? We need that green angle? Yes? Okay. We don't know that green angle. We know this angle, don't we? Okay, so we need to do something here that might be something you don't recall or haven't seen in a long time, or maybe you've never seen this. Yes, if you have two parallel lines, these are parallel to one another, and you cross through them with a line, then there's a relationship between the interior angles, and that is that alternate interior angles are congruent, which means that this angle here is the same as the one on the other side, like this. And then this angle here is the same as this angle here. Okay, we kind of can use that here because if we notice our x-axis and the ceiling, I guess, that's holding our ropes, that's like two parallel lines. So I could almost consider my vector R2 to be going like this, right? That's my vector R2? Or, sorry, R1 is what I meant to say. That's R1. And I'm trying to find out what this angle right here is, right?
Yeah.
But that means I need to find out what this angle here is. And I know that this angle right here is what? 45.04 degrees. And so if that's 45.04 degrees, all the way around is 180, right? From here all the way across. So I just need to take that and subtract it from 180. 130, what is it? 134.96 degrees. That is the angle of R1. That's the angle of R1. Questions? Sure? Mm-hmm.
Makes sense to me.
Okay. Now, let's figure out what the x and y components of R1 will be. So if we look at R1 is a vector. Its x component should be the length of the vector. The length of the vector, which is what? What's the length of this vector? 5 times what? Yeah, I think I heard it. No? Cosine of 134.96. So times cosine of 134.96 degrees. And then what will its y component be? Its length, 5, right, times sine of 134.96 degrees. Now remember, this is just coming from the idea that we learned a long time ago when we were learning about trig functions, that if you have a point, this is r and this is theta, then the x-coordinate is r cosine theta and the y-coordinate is r sine theta. That came off the definition of sine and cosine when we first introduced these trig functions on an arbitrary circle, not on the unit circle, right? On the unit circle, this is just cosine theta, sine theta. But on an arbitrary radius, you have to include the r in front of the cosine and the sine.
Professor,
Yes?
where did you get the 5 from?
The length of this rope is 5. So it's the length of the vector.
Oh, okay.
Yes?
CC.
Okay, now we have a little bit of an issue with this. Let's see if anyone catches it. Maybe I should put up here, what were we trying to find? Did I put that last time in the beginning? I put, what were we trying to find?
The forces on the rope.
The forces, the what? The forces on the rope, right? What does that give me right there? R1, if I write it that way, that gives me, I know the length is 5, right? And then I just got like how long this would be and how long this would be this, right?
Yeah.
These are the components, right? But does this have anything to do with force? Okay, what about the negative 200? Is the negative 200 a length or a force?
Force
It's a force, right? Don't I need
to incorporate it.
the force of this vector, right? And the force of this vector, which is the length of the vector, right? Is that the length of the rope, though? It is not the length of the rope. So what's wrong with that?
You have one representing force and you have one representing length.
That's right. So are we talking about length or force here?
Force.
Force, right? So
It needs to be 200 cosine.
you're catching it. This right here, do I want this to be 5? What do I want it to be?
0.
We need to call it something, all right? Let me draw something right here so you can see it. This is the problem that we had when we first put the problem up on the board last class, is that we can't confuse lengths with forces. Those are two different things, right? If I'm holding, if the rope is sitting there holding that weight, how long the rope is has nothing to do with how much tension's on the rope, right? I mean, in terms of yes, it does because it changes the angle if I change the length, but 5 has nothing to do with the force. It's just the rope's length. So let me just draw this picture again in a more simple format. We have a vector going this way, R1. We have a vector going this way, R2. And we have a vector going this way, which is G, right? That's what we have. Yes? What we want to know from last class, what we said is we want to know what the length of R1 is, or not the length, the magnitude of that, and we want to know what the magnitude of R2 is. Those were the two things we wanted to know, right? What do we know? We know the magnitude of G is what? 200, right? That's how long this vector is, the vector. Now, I understand that the rope is 5, but the vector itself is not governed by the length of the rope. You with me? So what should that 5 be in those formulas? It should not be 5. What should it be? An unknown, right? But what is it in terms of our picture and things we want to know and the things we don't want to know?
Magnitude.
The magnitude of what? R1, right? This 5, this is the most common mistake with a problem like this, is confusing rope lengths with forces. So although this This makes some sense. What this would give you is the x length and the y length of the rope. That's what this would give you. But we don't want that. We want the x component and y component of the vector. So the 5 actually should be magnitude of R1, which we don't know what that is, right? But it's okay, because we're going to use that. We're going to use that. We're going to be able to come up with 2 equations and 2 unknowns, and we're going to be able to solve. Let's see if doing the other vector makes any more sense. How about R2? What can you tell me about R2? R2 has 2 components to it. Now, do we know the angle of R2? This angle right here, what is it? 17.15, because again, we have that line cutting through the 2 parallels. And so this alternate interior, that means that the angle there should be 17.15. So that is 17.15 degrees. Now, in terms of the vector R2, not the length of the rope, in terms of the vector R2, what are the components? Magnitude of R2, cosine of 17.15, and then magnitude of R2, sine of 17.15 degrees. And then let's just write down G again. G, the vector G, was the vector 0 and then negative 200. Agreed? Okay. We have taken the 3 vectors we were given, right? We were able to determine the angle of the vectors through some law of cosines. And with that, we were able to come up with some general information about the vectors. I know the x component and y components of these vectors, but I still don't know the magnitudes or lengths of the vectors, which is what I want. But I also know, because this isn't moving, the sum of the forces in the x direction must be 0, and the sum of the forces in the y direction must be 0. That means when I take these 3 together and I add them up, I should get 0. And when I take these 3 together and add them up, I should get 0, right? So let me write those equations down. And this is where we're going to get our 2 equations, 2 unknowns. Okay, first of all, and I'm just going to put up here just for reference, I'm looking at the sum of the forces in the x direction, all right? Just to use a little bit of physics notation, that's what's going on here. In the x direction, I have magnitude of R1, cosine of 134.96, plus magnitude of R2, cosine of 17.15, plus what? 0. That must equal 0, right? That's my first equation. The sum of the forces in the y direction is magnitude of R1, sine of 134.96 degrees, plus magnitude of R2, sine of 17.15 degrees, plus what? Negative 200? So I'm going to just put minus 200, but that must be 0. All right, we're going to need our calculators, because cosine, that cosine's up there, we can figure out what those are. Those are numbers. Sine stuff, that's numbers. So I do cosine of 134.96. I get negative 0.7066. So rewriting this equation, I get negative 0.707. I'm going to round it. Magnitude of R1 plus, well, it might be, yeah, it is going to be plus. Now I take cosine of 17.15, right? 0.9555. I'll just put 0.9. Let's go 0.956. Magnitude of R2 equals 0. Y'all okay with that? And then I'm going to do the same thing, but now I'm going to do sine. So sine of 134.96 So I'm going to get 0.707 magnitude of R1. And then sine of 17.15. I get plus 0.295 magnitude of R2 equals 200. So I went ahead and moved that 200 to the other side. There's my two equations with my two unknowns. So at this point, you can solve one of them, right? What are the two ways that you can solve systems of equations? Do you remember the two methods?
X is subject or Y is subject. Oh,
Elimination and substitution. Those are the two methods for, maybe if I put it on the board, it'll look more familiar. If I put x minus y equals 5, and I put 2x plus y equals 12, and I said solve this, one thing you could do is you could take this equation, solve it for x or y, and plug it into this one, right? That's called substitution. The other way, see if this rings a bell at all, is that you look straight down your x's and your y's, and you see if you add straight down if anything would cancel.
Oh, yeah.
And so like in this case, if I add straight down, what would I get? Get 3x, the y's would cancel, I get over here 17. So 3x would equal 17. That's called elimination. And what if this was 3y here? It wouldn't work, right? So I could multiply the top equation by 3, 3 here, 3 here, 3 here, and then when I added it would work. Does that ring a bell, those two methods?
Yeah, these are like matrices.
And then you could use matrices also.
Yeah, what was the other one? Like the way they teach you to solve it. There's
Like a
another
determinant?
one.
Or no,
Yeah,
not.
A squared, B squared, C squared, I think it was, or something like that. You use the variables.
Yeah, so that's if you're getting into matrices. I'm just saying, without matrices, we have substitution and elimination.
And we can do an elimination.
The reason I'm bringing this up is why?
We have an elimination.
We actually have an elimination right now. Do y'all see it?
Yep, right there.
These two are exactly the same, but they're off by a sign. So instead of me going and solving this for R1 or R2 and then plugging it in here, which I could do, I noticed that since these are opposites, if I add straight down right now, I'm going to be there. So I'm going to choose to do it that way. So if you add these two equations straight down, this and this together is 0. And then you have to do those two together. So you have to do 0.956 plus 0.295, 1.251. So plus 1.251 magnitude of R2 is equal to 200. And now divide both sides by 1.215. Bless you. Magnitude of R2 is 159.87. And that corresponds to the length of the vector. Not the length of the rope, the length of the vector. And the length of the vector is the force. And so there's 159, about 160 pounds of force on that rope, even though the weight's only 200 pounds. So does that mean that there's about 40 pounds of tension on the other rope? No. We're about to see that. So how do we figure out what the other rope's tension is, R1? Yeah, we'll just go back into either one of these equations. It doesn't matter which one I go into. I'll just go into the top one. I have negative 0.707 magnitude R1 plus 0.956 times magnitude of R2, which I just found was 159.87. And that must be 0. So I'm just going to multiply these together, move it to the other side, divide by negative 0.707, and I'm going to be there. Does anyone have a question as to what I'm doing? No, you should get a positive because this is negative, right? So these will be positive, move it over, it's negative, divide by negative. Oh, magnitude of R2. I'm getting 216.
No, that would be R1.
It is R1. I don't know why. Thank you. 216.18 or so. And this is pounds, right? LBS, pounds. This is also pounds. So the tension on the ropes is actually higher, like this one. The tension on rope 1 is higher than the actual weight of the box itself. And that's like we were doing that thing where you grab one end, I grab one end, we try and pull. Like how much force is it going to take to bring something up straight? An infinite amount of force is what it would take. Okay. Can we put this to sleep? Yes. I have one more problem to look at. Let's say that we have a tightrope walker. Okay, tightrope walker. And when the tightrope walker is on this rope, the tightrope walker is going to deflect the rope, right? There's going to be some deflection on that rope. Let's say this tightrope walker is a 165-pound person. And let's say that we're able to measure the deflection of the rope. So let's say that there's only like a 2-degree deflection there. And over here, let's say that there's a 3.5-degree deflection there. Understand?
Yes, sir.
Okay.
So what is that? Would you mark green?
The weight of the person? Oh, what the dotted line is straight across. From pole to pole, straight across is there, but because he has weight, he's going to deflect the rope down. So the question is asking about the tension here and the tension here. All right? So let's look at forces. We have the same, this is the same exact situation we just had. It's the same problem kind of formulated in a different sort of word problem. Do you see 3 vectors?
Yes.
Okay. The vectors are
R1, R2.
the gravity or the weight of the person, let's call it G. You have the vector out to the left, right? And the vector out to the right. And let's call this L, vector L and vector R for the left side and the right side. How about that? Now, we're going to have to come up with the components of these vectors. And then remember that the sum of the forces in each direction, x direction and the y direction, has to be 0. Now, do I know the angle for the vector R? What is the angle right here? What is it? 3.5 degrees. Do I know the angle for this vector? Now be careful here. It's got to be relative to the x-axis. So what is the angle we're talking about? It's this angle, right? That angle right there. That's going to be, what do you say? 178. I thought I heard 378. Yes, that's 178. Because it's 180 all the way across, right? And it's only 2 degrees. And I'm using that parallel thing again, aren't I? Like if there's a parallel, if the angle here is 2, then the angle right there is 2. If the angle right here is 3.5, then the angle right here is 3.5. Everybody good?
178 is the angle for the R vector, right?
For the L vector.
L vector.
L vector. The L vector, the angle for it is 178, not 2.
And for R, it would just be 3.5.
Yes, and think about this. This L vector, the x component, right, should be negative. And if you're using 178, cosine of 178 is going to be negative. But if you used 2 degrees, cosine of 2 degrees is going to be positive. So it's going to think that your vector is also pointing in this direction, like both of them are pointing in this direction.
The vector has to start from the positive
It's always
side,
you're always referencing the x-axis to form your angle,
not
not the other side. The positive, the standard position of an angle is out the positive direction on the x-axis. So all our angles will be relative to that. Okay, maybe this will go a little faster. Let's try and come up with the components of these. How about G? G, 0, negative 1. What is it?
You put 165 as the first square.
I did 65? Okay, negative 165.
I mean, if you want to change it to 185.
Nah, we'll leave it. How about vector L? Tell me about vector L. Magnitude of L, cosine 178. Okay, and then magnitude of L, sine 178. And then for the right vector, we have magnitude of R, cosine of 3.5 degrees, and then magnitude of R, sine of 3.5 degrees. We know that the sum of the x's has to be 0. We know the sum of the y's have to be 0, right?
Yes.
Okay, so there's your two equations. Let's put them together. I have magnitude of L, cosine 178, plus magnitude of R, cosine of 3.5 degrees, plus 0, right, equals 0. Magnitude of L, sine of 178, plus magnitude of R, sine of 3.5, plus, it's actually minus 165, right? So I'm going to just say equals 165. I'm going to take that over to the other side. Now, calculator. Cosine 178. So I'm getting negative 0.9993. I better take a couple. I'm going to go about, let's go 5 decimal places on this one. Because it's such a small deflection, if I round too much, it's going to think it's straight across or something, and that's not happening. So that times magnitude of L plus, let's see, cosine of 3.5, 0.998, 0.99813, magnitude of R must equal 0. Sine, I'm going to do the sine ones now. Sine of 178 is 0.034. I should round that to 9, but I'll just say 89. Magnitude of L plus, now we're doing sine of 3.5. 0.06104, magnitude of R must equal 165. So this system of equations became this system of equations. Am I going to be able to do elimination like I did last time? No, unfortunately no. So yeah, let's just solve this top one. You want to solve it for L? Yeah, solve it for L. So that means I'm going to take negative 0.99939 magnitude of L, and then equals negative 0.99813 magnitude of R. Just move that over to the other side, and then divide. .99873, 874. So magnitude of L equals 0.99874 magnitude of R. Then I can plug that in to the second equation here, right? So we get 0.03489 magnitude of L, which is actually 0.99874 magnitude of R, plus 0.06104 magnitude of R, I'm running out of room, equals 165.
Got 0.0485.
Did you solve the whole thing?
Oh, no, for
No?
the,
Oh.
the times
These two?
yeah,
You got what?
0.3485.
Okay, we'll trust that. Magnitude of R plus 0.06104 magnitude of R must equal 165. So now these are like terms, so you can add them.
And
So you should get like 0.09588 or 89, whatever,
and then
magnitude of R.
magnitude of R equals 1,720.90.
So now divide both sides. So you get magnitude of R is some crazy number, 1720.7.
Oh, I forgot the 0.9.
0.9. It's all right. Close enough. We've rounded quite a bit. So basically, you need to make sure that so far, that cable, right? So far, that rope has got that much tension on it. It only weighs 165 pounds, right?
Very strong rope.
That rope needs to be able to support 1,700 pounds. Now, so far, that's the right side. The left side, let's see what the left side is. So what about the left side? The left side is 0.99874 times R. So you take that number and multiply it by this. It's going to be a little less, isn't it? So L,
1718.73.
1718.7 pounds. So if you've got this rope, and you plan on walking across it, right? With that much deflection in the rope, it needs to be able to support that much weight. You all right?
I was just trying to see where L came from real quick.
Oh, back up to this formula right here. We solve for L, and we already know what R is, right? R, the magnitude of R is this, so we just plug it in right there, hit it with that number, we're done. Okay. So a lot of times, like when it comes to ropes and cables, like if I told you I built a zip line a few years ago, so as you might imagine, I ran some calculations first. I estimated my, how much sag there would be if someone was on it, and then, measured some angles, and you can get like loads, like maximum loads. And then you also have to take into the fact, like, what if someone like jumps off the platform and, it's different than just slowly applying a load and then going. If you jump, then that's much more load.
Just put a sign
So,
saying don't jump. Jump.
Well,
It's at your own risk.
it worked. I think I was using, I want to say I was using half-inch. I think I was using half-inch aircraft cable for mine.
Did you buy a puller? Or did
I had
you
a puller.
just-
Yeah, I got a
you
puller.
fence puller?
Yeah, no, I had a come along
Yeah.
that has the actual cable puller on it, so you can pull it. And then I had, what are those called, turnbuckles?
So you just kind of
Yeah.
estimated the amount of force you put on it.
And then like multiplied by 3. Yeah, like I over-engineered everything,
That's what happens when
The
you're.
tree was going to come out of the ground before the cable was going to break. So anyways, that's a lot of tension in that rope, isn't it? If you buy rope from Home Depot or something, a lot of times it'll say like maximum working load. And that maximum working load is what that rope is designed to be, what tension that can be under normal conditions. It's not its braking load. The braking load is something different. It's usually a lot more than its working load, right? So the working load might be 500 pounds, but it might take 1,200 pounds to break the rope, because you don't want to be right on that threshold of braking, right? You want to be way below the braking load with your working load. All right, I want to leave at least 30 minutes to talk about the test. So give me about 20 minutes now. We're going to talk dot product. So
Not on the exam, right?
this is not on the exam, but it'll be on the final exam. Yeah. So dot product. These are the notes that I took from my Cal 3 class. So these are not gonna, does not correspond to the section in your book, but if you're following along in your book, we are talking about section. What's that? They did teach this in pre-cal? What? Since when? We're doing a little different in this class. We started with trig right away. We didn't do any conics. We didn't do any partial fraction decomposition. We're going to do that at the end. So I'm trying to get through dot product and other stuff. Okay, so dot product. Let's see if you remember this. This has been a long time. If you have a vector, let's call it vector v, you can multiply it by a number, c, and that's called scalar multiplication. We've already done this, scalar. I told you that there were 3 types of multiplication with vectors. Scalar, and then 2 others, dot product and cross product. And I said we won't talk about cross product because that requires 3-dimensional space, and all we're going to work with is 2-dimensional space. So now we're going to look at the dot product. And the dot product is what happens if you have 2 vectors. Let's use v and u or something like that. What happens if you take 2 vectors and try and multiply them together? How do you do it? What does it mean? All that good stuff. So first of all, if you're given 2 vectors in 2-dimensional space, so like v and u, and you want to dot them together. So v here is a vector. It has 2 components. We'll call it v1 and v2. U is 2-dimensional. It has 2 components, u1 and u2. Then the dot product, okay, we use this like bolded dot. It's not the same multiplication dot. You know how when we write like 2x, we don't put that dot there? But it's understood. When you do a dot product, you have to put that dot there. And it's a different dot than this dot, because it's not your standard multiplication. It's vector multiplication. So big dot here. Dot product. But how do you actually compute the dot product? What you do is you take v1 times u1 plus v2 times u2. Now these multiplications are your standard multiplications. So all you're doing is taking this number here times this number plus this number times this number.
Just going to be one number.
And then your answer at the end is going to be a number. And do y'all remember me talking about how like everything we've done, it's always been like put 2 dogs together, you get a dog, 2 cats, you get a cat. This is that first time that we ever have 2 vectors, some operation, and our answer is not a vector, our answer is a number. So the dot product is the sum of the products of the components of the vector. It's vital to notice that the dot product yields a number as an answer, not a vector. We use a bold dot to represent the dot product as opposed to the regular multiplication dot. Okay, that's it for 2-dimensional dot products. So we're going to do an example, but I'm going to have to make up my own. I'll just adapt those vectors up there. I'll just cut off the other component. So let's do v is 2, -3, and u is -3, 4. Okay, so you got 2 vectors. And I want to find the dot product. Find v dot u. So for us, what will this be? 2 times -3. So I'm going to write that down. 2 times -3, and then plus what?
Negative 3 times 4.
-3 times 4. So I'm doing 2 times -3 plus -3 times 4. Let's see what we get. -6 plus -12 is -18. Right?
That's it?
That's it. Okay, now what is u dot v? So if I change the order, does that change the answer?
No.
The only difference is that instead of doing 2 times -3 plus -3 times 4, I'm going to do -3 times 2 plus 4 times -3, and it just flipped this order, didn't it? And in multiplication, standard multiplication between numbers, the order doesn't matter. Do you all know what that's called? That property? Where you can change the order?
Commutative?
No, commutative. It's the commutative property of multiplication. Commute, you can flip the order. Okay, so because we can flip the order, we should get the same answer, and we do. We get -18. And that works for any dot products. So the operation of dot product is commutative. It does not matter. The order doesn't matter how you do it. All right? So here's some properties of the dot product. All right, so look at these. First of all, if you dot a vector with itself, what would happen? So if I take the vector u, which is u1, u2, and I dot it with itself, so if I take u1, u2, and I dot it with u1, u2, then you're going to go u1 times u1 plus u2 times u2, right? Which I don't write up here, but this would be u1 squared plus u2 squared, wouldn't it? That's what it would be if I dotted a vector with itself. Yeah? Now, do you remember this from a couple of classes ago? What is the magnitude of a vector? The root of the squares of each of the components. That was from a couple of classes ago. The length of a vector is the square root of the square of the sum of the components of the vector. So do you see how the dot product, if you dot u with itself, we get this, right? Isn't that really close to this? This is actually that up there squared, isn't it? Because if I square square root, the square root goes away. This is the length of u squared, and that's what this is saying right here. If you dot a vector with itself, it's equivalent to the length of the vector squared. Second property I just tried to convince you of, that u dot v is the same as v dot u. That means that the dot product is commutative. We also have a distributive property of dot products. If you take two vectors and add them together, you get a new vector, don't you? And if I dot that with u, I get an answer. This says that you can take the dot product and do a dot product distribution. So instead of adding these together first, you can actually just dot these two, dot that one and that one, and then add those two answers and you get the same result. We won't verify these. We're just going to look at them as properties. Property 4 says if you have a number, this is scalar multiplication, a vector times a number, right? A vector times a number, get that answer, and then dot it. You could have, if you wanted to, taken that scalar and pulled it out, dotted them first, and then put the scalar in. Or you could have even moved that scalar from this vector to the other vector. So the scalar can slide around, basically, can move around. The zero vector dotted with any vector is 0. Not the zero vector, is the number 0. Now you have to be asking yourself a question by this point. No? Like I'm showing you how to mechanically do the dot product. But maybe you have a question about it?
Why?
Like, okay, like what does it do, right? Like what's the usefulness of that number, right? So big deal, you get two vectors, you do this thing called a dot product and gives you a number. Like what does that number mean, right? Like is it even useful to us? Yeah, this is going to be the one I want to show you. Well, there's a theorem, okay? Here it is. If theta is the angle between two vectors u and v, so let's say I take a vector u, and I take a vector v, doesn't matter where this is, then there is a smallest angle between them, which would be this angle theta, right? So any two vectors, remember vectors can be moved around anywhere I want, right? So if I move them around so that they're tail to tail, then they must form an angle between them, right? Okay. What if I open them up? That angle between them is getting big, right? It's obtuse. It's bigger than 90. And then what happens if I go directly across from each other? It's 180. Now what if I go like further like this? Now look at the angle between them. We're actually talking now about this angle, not that angle. So when we talk about theta, it's the smallest angle between the two vectors. So here, that would be theta. If I come around and I'm down here, theta is right in here. Do y'all see that?
Yep.
Okay. So theta is always going to be between what and what?
Two vectors. This is the
What's the smallest theta could be? What's the smallest it could be? 0. That would mean they're pointed in the same direction. And the biggest it could be would be what? 180. Okay? That would be the restriction on theta. Because once you go past 180, right, you're now talking about an angle down here that's between them is smaller than 180. Okay, this is an outstanding theorem right here. It actually gives you a meaning for the number. Okay, we know that if we dot two vectors together, this is a number, isn't it? That's a number? That number is equal to the length of u, that's this vector's length, times the length of v, right? Times cosine of the angle between the vector. Now, I'm not going to prove to you why this is true, all right? Theorems means there's a proof. So I'm not going to prove this to you. We're going to take this on faith. Is that all right? Let's see why that is useful to us. Given two vectors, the angle and the angle theta between them, the angle must be between 0 and pi, which is what I was just trying to convince you of, right? Y'all are okay with that? We don't need to answer that question, why? Okay. Now consider the cosine function from pre-calculus. Restricted to the interval 0 to pi. So think about cosine just between 0 and pi, right? When theta is 0, we know that cosine is 1, right? This means that if the angle between our vectors is 0, they're pointed in the same direction, right? So the angle between our two vectors, if it's 0, the angle is 0, cosine is 1. And that formula that I had up on the board a second ago, u dot v equals magnitude of u times magnitude of v cosine of theta. So if theta is 0, this is 1, then that means that the dot product is actually just the product of the lengths of the vectors. That's all it is, right? That's all the dot product would mean if they were pointed in the same direction. Still, who cares, right? Like who cares?